work. That's timings. That is so this is the type of results that you can find in the paper. Speed up. So this speed up, I didn't show it, but again, speed up we have up to 256 processors. That's the spiral sources on a space filling curve down here. Okay. Then you have the spiral sources on the with our load balancing scheme with the crosses, and then you have a uniform distribution. The top two ones with 4 million and 10 million.
Okay, so the top ones are uniform distribution as versus uniform. Something that's not quite.
This one is the speed up, and this one is efficiency, and this is the load balancing. So now we have numbers, and there's the 1 and 0 and so on. So and here is our legend now. So the spiral are the two ones down here.
Okay, thank you.
Another NCSA question.
I missed what you used for the graph partition. Did you say
Archimedes?
Archimedes,
okay,
yes. Thanks.
So that's the great thing about open source. You know, we were able to use an existing and tried and tested tool for the partitioning. So let me go back now to my talk. Where are we? I think undo is what is called for here. Undo, delete. Okay, good. There. So this is a summary of these results. For the uniform distribution, we find 2% deviation of processor time when you look up to 64 processors, and within 20% up to 256. There's a final degradation there in the 256 processors. For the non-uniform distribution, we're within 20% in time from one processor to the other, up to 256 processors, and we see that it outperforms the space filling curve. And here's the answer to Professor Wu's questions about the cost of the load balancing approach, which is here a measure of 0.5 of the total execution time for these experiments. So that's the summary of the work we've done in the parallel implementation of the fast multiple method. And here, let me say that it's all open source. In my group, we're very committed to developing all of our codes in the open source scheme, even if they're ugly. And the research code, when the paper is ready, as soon as the paper goes on archive, we try to have the code in Google Code, even if it's ugly. Okay? Yes?
So I assume that the results are based on a cluster execution?
Yes, this is a cluster of, you know, it's a sort of a old cluster, you know, 3-year-old.
So any preliminary results on executing on a GPU? I imagine that you will have some.
We have some. Yeah. Yes, we have some. We have some on GPU. Yes, coming up.
Great.
Okay, here's my scaling speed up. I already showed you that from the paper, and here's the link to our website, and you probably can Google it as well. So again, the serial code is on Google Code. On Python, there's a Python first research code that we had, you know, 3 years ago. Then the parallel code has been developed in collaboration with Matthew Nepley, who is one of the developers of the PETSI team, and from Argonne, and he's now at Computation Institute. And so he's, you know, of course, quite an expert in library development and maintenance. So it's through that, well, you know, supported through this friendly kind of email list sort of way. Right? It's not a big open source project. It's just a friendly handful of people. So, but we do answer to requests for support, friendly requests for support. Okay, so that's the fast multiple method on a parallel and regular MPI approach. So I'm going to give you now a simplified view of the FMM on GPU. And this is, I'm going to describe it based on some work that we just finished and submitted to the GPU GEMS volume. And we started by, to produce this work, we sort of wanted to be consistent with the previous work on N-body, which was published in the GPU GEMS volume 3, which presents the all pairs evaluation, the embarrassingly parallel one, right? And this is the chapter, a snapshot of the first page of that chapter. Is available online, as many of you may know. And this is our title. And we've tried to be consistent in terms of some of the nomenclature and so on. So let me use first, I wonder if you can see the lines are a little bit thin. This new graphical overview of, because this work presents both the tree code and the fast multiple method, which are a little bit different. So here again, we start from the bottom where you have the source particles. We're going up the tree. We sort of representing in this sketch the subsequent steps you have to do in the algorithm, and following this in the arrows. Sorry about that. And first, you create the multiple expansions. This is a particle to multiple operation, which is done both on the tree code and the fast multiple method, FMM. Then you cluster those series expansions at the higher levels of the tree, aggregate those in what's called the multiple to multiple, again, M to M, done both in the tree code and FMM, fast multiple method. Then the tree code first. Let me show you the tree code first. The tree code does not do the local expansions. Goes straight from the multiple expansions to the particles and does what's called the multiple to particle interaction. And then finally gets the answer of the field just using multiple expansions. And in contrast, the fast multiple method uses this additional mathematical tool, which is the local expansion. So it does the multiple to local transformations, and then local to local, local to particle, and finally we have the particle to particle, which is the all pairs interaction that always has to be done for the near field. For all the particles which are near an evaluation point, we still have to do the all pairs, but it's a small region of space and it does not dominate, so the complexity can be brought down to order n log n and n. So that's an overview, and let me describe the implementation on the GPU. So first of all, the all pairs interaction, sort of the same way that is done in the Nyland chapter for GPU gems, consists of parallelizing the in terms of the sources. The targets. So we're going to each thread is going to evaluate one target, and you see the rows in this picture represent the parallel work that is done. P threads are done in one thread block here. And going down, this represents the different thread blocks. N is the number of particles, so N divided by P is the number of blocks we have. All of the target points are supposed, in this picture, associated to a row. All of the evaluation source points, are represented by the columns, and those are done sequentially. They could be the same set of particles, or they could be different, so it's left open to those possibilities. So the sources are moved from global memory to shared memory in chunks of P. And the idea is that you need to have a big enough problem that you can have many parallel threads so that those transfers of data from global to shared memory can be overlapped with enough work. So the targets are performed in parallel. The sources are done sequentially. Each one of these thick lines represents a synchronization point where you've finished calculating P sources on one evaluation, on the evaluation points locally owned by a thread block. And then you synchronize, bring in another chunk of P, do your evaluations, synchronize, bring another chunk of P, do your evaluations, and so on. This is the very broad brush idea of how the all pairs interaction is done in the Nyland n-body solver. So, and the size of P is determined to get the maximum performance. Nyland, in their GPU gems chapter, experimented with different values of P and found that they could get an optimum result with 256. You can also use, say, occupancy calculator to find what is the optimum size of P, but it turns out we're using 256, just the same as Nyland. So we're parallelizing on targets. We're assuming in this example, by the way, all of this is from the GPU gems chapter, which we just finished, and we're happy to share the PDF preprint of that also in the Google groups. So you can see this, more details about that, and the code is also already on Google Code, so you can read the code for this. We're assuming that all of the n particles can fit in global memory, and we transfer to shared memory in chunks of P. Small subsets of sources are moved in a coalesced way to shared memory to interact with targets. So you can see that the all pairs is not very hard to understand. So now we're going to use that same model of working on the GPU for the different stages of the FMM. So obviously the P2P, particle-to-particle interaction, which is done at only the local near field in the FMM, is the same as the all pairs. There's no difference. The only difference between the all pairs and the FMM P2P is that in the FMM P2P, each target interacts with a different set of sources, right? So in addition to knowing the location and strength of the sources, we need something else. We need to know an offset to know where to start reading the own sources. I mean, each particle has their own interaction list. In the all pairs, all the targets evaluate with all the sources. In the FMM, we only evaluate with a subset, which is indicated in this picture here. But once we consider that, the rest is the same. So we parallelize on the targets. Each thread calculates one target. And so if we're doing the targets in this red box over here on the left, represented here, then we're going to move in chunks as well into the shared memory. Say this is going, all of this here is going to represent the near field of this box, and the different chunks are sort of represented by the different colors, indicated that they're moved to shared memory sequentially. And a different evaluation box will work the same way. This is the evaluation box here in purple, which has all of the boxes around it as its near field, and these are again moved in chunks of P, and each thread calculates one target. So this happens at each leaf level of the tree. Okay, that's the P2P. So that's the easiest to understand because we're going from the all pairs to this one. You can see the analogy there. So now imagine that we're going to do the the interaction between the multiple expansions and certain targets, evaluation points. So now it's the same thing again, but the only difference is instead of moving particle information in terms of location and sources, we move coefficients. The coefficients of the series expansion that represents the multiple, the coefficients of the multiple expansion that represents the sources in the interaction list, what's called. So now, for example, all of these purple boxes over here, instead of moving all the particle information, the microscopic, if you will, particle information, we're going to move the series expansion, just the coefficients that represents each box, into shared memory in chunks of P, or calculate there the chunks in terms of now it's a different amount of data that you have to calculate. But again, the targets are performed in parallel, and the sources, which in this case are multiple expansions, are done sequentially. And so you can see that it's all sort of based in the same idea of the all pairs. And we're trying to present this in this kind of incremental way in the GPU GEMS article so that you can follow it and understand the code. I have a couple of slides showing the code now and some of the mathematics, but I'm just going to really gloss over that because I don't want you to get scared or anything. It's all described. You just have to have a little bit of patience. Basically, the main mathematical difficulty in the fast multiple method is that you need to use spherical harmonics in 3D. And so this is a little bit tough to chew, but with a little patience, you can get through it. So in the direct evaluation, the potential looks something like this. In the fast multiple method, you have this kind of mathematical beasts. You have the multiple expansion, which is a function of the spherical harmonics, and this multiple expansion goes in the summations and so on. But in the end, the evaluation of the potential has a similar form to the other one. Okay, it just has this more sort of elaborate mathematics in it. And I'm going to just show you this slide. I know it's very busy. I don't want you to actually try to read it. I'm just going to, you're going to have a PDF of this. And the reason for showing this in one slide is because then I'm going to concentrate. I mean, everything is color-coded, so you can follow it. I'm going to concentrate on this area over here that is colored, and then I'm going to zoom up to that. Okay? So this is just a sequential sort of thing that you can follow on the PDF. So I'm zooming up to that because the listing of the code, this is the whole listing. Okay, it's whatever, 46 lines, and I'm just going to concentrate